So, in this way, using the NDTM of A, NDTM M of the problem A, we can convert any input instance to a graph instance. And in the graph, all you have to do is find a path from, check whether C start to C except there is a path, right. There will be a path if and only if X is a yes string of A, and all this can be done in the reduction is actually implicitly L computable. Remember that we call it implicit because this work tape is too small to store G comma S comma T. So, we cannot store f of x, but we can access any bit in that much of workspace. So, overall this means that we have reduced A to path. Okay, as claimed. And lemma 1 and lemma 2 now, they together give you that path is NL complete. Okay, so directed reachability is an NL complete problem. So, solving it fast means, solving it better means that you are actually simulating L better than the trivial. That is an open question. Whether NL equals L, that is an open question. A corollary of this theorem is that complement of path, this is coNL complete. Right. So, path is NL complete. So, for the co-class, you take the complement, that will be coNL complete using the same reduction. So, by the same f. So, directed unreachability, that is the hardest problem in coNL, and the question you can ask again like NP coNP, whether these two things are equal, whether NL is equal to coNL, and here there will be a big surprise that we will actually be able to prove it. So, we can actually prove that NL is equal to coNL, and of course, we do not know whether it is L. So, let us look at this amazing proof, NL equal to coNL. So, this is a theorem by independently proved by two people. So, Immerman and Zlepzeny. It is an old result, but it was a stunning result, because a priori people thought that NL equal to coNL should be like NP equal to coNP question. But in this case, actually, because of reachability being such a special problem, directed unreachability actually converts to directed reachability, making NL equal to coNL. So, let us look at this nice proof, this elementary proof. So, what we will show is it suffices to show that path complement is in NL, right? Unreachability is in NL. So we design a log space algorithm A such that for input G comma S comma T, there is a sequence of guesses U for A such that A will accept. A will accept if and only if S to T there is no path. Okay, so note this negation. So S to T there is no path in the graph G, input graph G, and in that case there will be a certificate U for A which A can verify in log space. Right, that is what we will design. So how will we achieve this? So the idea is simple to state, it is just by path counting. So count paths in G. Okay, so it's by path counting. So let's implement the idea. Let me specify more that count paths of length equal to I in the graph G. Okay, so it will be a detailed path counting in the given graph. And the certificate U will be based on that. Is based on these counts. So let's do this. Let's implement this. So let N be the number of vertices and Ci be the set of vertices reachable from S in I steps, at most I steps. Okay, so remember this important object Ci, it's the set of vertices which are at distance at most I from the source vertex. Now immediate observation is whether V is in Ci for a vertex. Okay, this question is in NL. This is certifiable in log space. This question, why is it in NL? Well, because if V is in Ci, then there will be at most I vertices leading you from S to V. So you can just guess them. One by one you guess them. And just like we showed the path in NL, the same thing. Same proof works, right? That you remember. So let's now design a log space machine. Let's now certify the following in log space. So these will be more interesting. The first is complement of this, right? V not in CI. How about that? That is what we are interested in the theorem statement. So we'll do this given the size of CI. So vertex V not in CI given CI size, and now how will you find out the size of CI? That also you have to do in NL, right? At least you have to certify it. So let's certify this. So CI equal to C given the previous one, size of Ci minus 1, and obviously C. Okay, so vertex not in Ci, for this we'll actually use the count, the size of Ci, and to compute the count or to certify the count we'll use the previous count, right? So it will be a kind of recursive algorithm. But remember, it's just a certification, so it's not computing C, it is just certifying, right, whether this is the correct answer. So if we do this, do both these things in log space, then this will imply that path is in coNL, or the complement of path is in NL, right, which will mean NL equal to coNL. Why is that? Well, because that's what it is checking. It is checking whether T is not in Cn, right? That would mean that S and T are disconnected using Ct, and Ct itself it will verify by guessing its size, which it will verify by going back to Cn minus 1. Right. So Cn minus 1, Cn minus 2, those guesses can be made. So by this non-deterministic log space machine, you can ultimately check whether T is not in Cn. So these 2 points, 1 and 2, is all we have to now verify. So let's do it. So certifying V not in Ci given the size. Okay, so how is that done? So the certificate of unreachability here, this will just be guess all the vertices which are in Ci. Once you have guessed them and verified them, just check that V is not there. So the certificate is simply the list of vertices V1, so ordered, let's say, of ordered vertices the certificate is an ordered list of vertices V1 less than V2 dot dot V the size of Ci such that all of them are in Ci and none equal to V. Right, so this will be this is clearly a certificate for V not in Ci. You know all, I mean, you just guess all the vertices in Ci in this order, and none of them equals V, and they are size of Ci many. The only thing is, how do you verify that your guesses are correct? So the verification will be as follows, or well, yeah, how do you correctly guess these? So to do this, guess Vj guess Vj plus 1 and then check guess Vj less than Vj plus 1 and check that both of them are in Ci. Right, that was discussed before. Any vertex can be verified to be in Ci, right? That is by the path problem in NL. So check whether Vj plus 1, both of them are in Ci, and then finally check that Ci many Vj's were correctly guessed. Right, so that's a log space machine which can guess the whole of Ci, everything, all the vertices it can guess. Remember that it doesn't have to store it, right, because it is going in this order, so it will just keep reusing the space. So reusing of space is important here. Otherwise you will be out of space because Ci may be n in size. See, the trick is that during this NDTM will just guess V1, remove it, or guess V1 and V2, and then guess V2 and V3 and V4, V5 and V6 and so on. Okay, and keep checking each time whether that particular vertex is in Ci, and you have done this Ci many times. So keep a counter for that. So this is then doable in NL. That's what you learn. So it only takes log n space. And what have you achieved? You have achieved point number 1, certifying V not in Ci given the size of Ci. Next is to actually compute this size by guessing. Right? How do you check that your guess is correct? Size of Ci is C. Let's do that now. So certify So next what we will do is, okay, let me change tactics here. So 2 will be done in 2 steps. So first what will be done is certify that V is not in Ci given the size of Ci minus 1. Okay, and after this we will show how 2 will be done. So let's do that. This will actually not be very different. Here you are given Ci minus 1 size, not Ci, but that is just moving to a neighbor. Okay, so it's the same certificate will be similar. So again the certificate is again a list V1 less than V2. It will be shorter now, VCI minus 1. All of them should be in Ci minus 1. None equal to V. Or V's neighbor. Right, so essentially here you have V and here you have a pre-neighbor of V, let's say U. So since you are looking at and here you have S, right, so basically these Ci minus 1 vertices, they are at distance I minus 1 from S, and you want to certify that V is at distance more than I, right. So neither V nor its neighbor U should be in Ci minus 1. Right, because if a neighbor is in Ci minus 1, then V also will be in Ci, so that you don't want. So hence both V and U should be out of this. So that's the only extra check. So once you do this, then you have verified V not in Ci. So to do this, guess Vj and Vj plus 1 again. Like before, right? And check that Vj plus 1 they are in Ci minus 1. Okay, so that's it. Finally check that Ci minus 1 many Vj's were guessed. So this is identical, almost identical to the previous thing. So even when you know Ci minus 1, that is enough to certify V not in Ci by ensuring that both V and its pre-neighbors, all the pre-neighbors and V, they don't appear when we enumerate Ci minus 1. Right. So this is again they are not being stored in the workspace, they are being guessed one by one and then checked that every guess is in Ci minus 1. and that these many Ci minus 1 many Vj's were actually guessed. So we guessed everything, and that's a certificate that V is not in Ci. Okay, so finally coming to item 2, which is certify that Ci is a given, is what one has guessed, C, given the length size of Ci minus 1. So how do you do this? Given the previous size, how do you certify that the current size is C? So yeah, the only way is you guess all the C vertices. So for every V in the vertex, V in Ci respectively V naught in Ci are certifiable in log space given size of Ci minus 1. It's whether a vertex is in Ci or not in Ci, this we have shown that given size of Ci minus 1, it's certifiable. Yeah, so do you go over all the vertices, that's all, and count, that gives you exact count of Ci. So go through vertices in that order, 1 less than 2 up to n, and count the correct size of Ci. Right, so that can be then checked with C, compare with C. So again, it will not store the vertices or the information, it will just store the count, and it will be able to certify whether Ci is indeed C or not. Right, so that finishes both 1 and 2, which finishes our proof. So both 1 and 2 are certifiable in L, which means that NL is equal to coNL. Right, 1 and 2 we have observed that it implies NL equal to coNL. So that finishes the proof of Immermann and Zlebzeni. Okay.